Okay, so I've gotten a lot of questions over how to do the graph portion of this, and specifically about the second derivatives and how hard it is. And basically, the gist of it is that you guys are going about it the wrong way. You're picking 5 graphs, and you're stringing them together, and you're trying to make them work after you have them together. You can't do it that way. You have to be more incremental. You have to consider things like concavity and how are you going to make it work. So I built the first part of a graph. I did it in about 30 minutes. I did it by myself without anybody checking my work. I just used Desmos to kind of check my graphs as I went to make sure they were lining up. And I just went from there. I had to use a lot of pre-cal knowledge in terms of shifting graphs and what I knew of them to make this work. Also, keep in mind that I reread through the project. I said that you had to have 5 portions that were continuous and differentiable. That means that the initial linear lift need not be. I mean, it needs to be continuous because you need to get people off the linear lift and onto the curve. They can't fall off the roller coaster. But it doesn't necessarily need to be continuous. And excuse me, it needs to be continuous. It doesn't need to be differentiable because you have an initial lift. You have a mechanical advantage. You have something that is pulling the roller coaster up over the thing and it's going slowly. So if there is a little bit of a jerk, they won't feel anything terrible. They'll feel like, oh, yep, I've hit that little crest, I've hit that piece, and we'll move on. Moreover, that portion of the roller coaster is not the main part of the graph. And so hopefully in this video you can see where I'm coming from. So this is my initial lift that I put into Desmos. It is y equals x. Okay? Now, I needed to have something that would go with this lift that would be basically the peak of my roller coaster because I wanted people to go downhill after. Well, I couldn't just do another linear piece. That would be a really sharp apex, and roller coasters can't do that. I needed something that was a little bit smoother at that point. So I went ahead and I created a parabola at this point that had a vertex at that piece. So essentially I realized, I basically want my parabola to do that. So I started at vertex form, and I went y equals negative x. Hey, look, my vertex is at 6, 6. Minus 6 squared plus 6. And I started there. And that basically gave me a parabola that went like that, and I decided that wasn't going to be good for business, and I wanted a parabola that went a little bit wider. And so I literally just fooled around in Desmos with this piece up in front to get the parabola fatter. I remembered that from pre-cal. If I fool with this piece, it will stretch and shrink the width of the parabola. I want my parabola to be wider. So I went to Desmos and the Desmos picture. Eventually what I ended up with was this. Now, the neat thing about Desmos is if you put it in Desmos, you can put the function like y equals x, but then you can put the little curly Q brackets and basically put in a domain. So I said I wanted my linear function to go from 0 to 6, and then I brought in this parabola. And the parabola function I actually ended up landing on was negative 1/4 x minus 6 squared plus 6. And if you simplify that all out, it was a negative 1/4 x minus 3x plus 3, I believe. I will double check and make sure that was what it was. Of course, now I can't see it. Yeah, no, plus 3x minus 3. Plus 3x minus 3. All right. So this is where it got harder, but not impossible. I thought, remember the first thing I do to tell you guys to do with a word problem is think about the problem. And I realized that this is a concave down shape. Concave down has a second derivative that is negative. I have no prayer of getting a second derivative the same if I pick a shape that is by nature concave up. I can't put another parabola here that's facing upwards. I have to consider the parts that are both decreasing. I need something that's both decreasing and concave down. So I thought about it for a second and I went, wait a minute. If I focused on a cubic, but not the whole cubic, because this is concave down, how would those two pieces right here and like right there. How would those go together? But then I thought about this piece right here and how this is concave down right at this point. Oop, nope, 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 I didn't mean to do that, sorry. This piece right here is concave down, right in there. And then it flips to concave up. I just need it to be concave down long enough for my acceleration to match. That's all I need. So this concave down part here could match with this concave down part here, and then it swoops back up and goes up to concave up, and life is good. In this pink part, in this initial part of the pink, I am both concave down and negative first derivative, decreasing as well. So that will match up conceivably. I just need to find where on this curve I can actually find that point. So now I have a target. I'm like, okay, I'm gonna put, I want this part of the x cube. Now I need to figure out a graph that will connect with this and give me the x cube. I need to meet the two parts together. Okay, so before I've done anything, I've really kind of thought this whole thing out. And so then I go about it a little bit further. So then I went, okay, if, let's call it f of x was my negative 1/4 x, what was it, squared, plus 3x minus 3. I knew that f of 10 was 2. So then I found the derivative, and I found that the derivative at 10 was negative 2. And I found that the double derivative of 10, second derivative of 10, was negative 1/2. Now I have targets. Because I know that my g of x, whatever it is, means that g of 10 must also be 2. G of prime of 10 must be negative 2. And g double prime of 10 must be negative 1/2. So what's g? That's the part I have to figure out. So I made g of x equals ax to the third plus bx to the second plus cx plus d. And then I had to think, because I had to basically create a system. G prime of x is going to be 3ax squared plus 2bx plus c. G double prime of x is 6ax plus 2b. And then I had to implement these constraints, is what they call them in the linear programming world, which is what you're doing here essentially. You had to implement these constraints. I put in the 10 for x, and I had an equation that was made up of a, b, c, and d. I had a 10 for prime. I put the 10 in for x and set it equal to negative 2. And then I put a 10 in for x and set it equal to negative 1/2. And then I used substitution. I solved for b in this case because it was the simpler one. And I found out what b was in terms of a. And then I solved for c in this case. And I used what I found in here for b. So I had c in terms of a, using this one from down here and this one together to cancel out the b. Then I used all that information into here, and I was able to simplify this top equation down into something that was just in terms of a and d. And then I just picked an a, because I had two things, and that's what we call a system with an infinite number of solutions, because I have two unknown variables. And again, this is getting into actually linear algebra, so this was my main area of interest in graduate school. But I had two variables. I had an unlimited number of options at that point. I could have picked anything, but I knew what a and d were. So I picked a as 1, because that seemed easy. And then I figured out what b, c, and d were in terms of that. And what I came up with was, when all was said and done, let me see if I can shrink this down. Nope. I'm going to do it this way. What I came up with was this equation, x to the third minus 30.25 x to the second plus 303x minus 1003 I know, it looks ugly, right? I would have never guessed to do that in a million years. That's why I had to use algebra to figure it out rather than just guess. Then,
It's obvious.
okay, so that black piece is my graph. Look, it matches brilliantly. And then, because I didn't want to get an F on my project, I actually went back and calculated the first and second derivatives for both the purple graph and the black graph, and they indeed matched. So it works brilliantly. And one of the things that I said in your project was that each portion that you needed to include needed to have both some kind of an interesting piece, okay? At least one. In this case, in the first graph, I do have my maximum, especially if I write my graph to be like this. Oh, no, not 2x. It was just x. It went from 0 to x to 6. Notice I'm not including 6. y2, which was, what did I say, was negative 0.25 x minus 6 squared plus 6. I'm going to say that goes from 6. Now notice how I'm including 6 as part of that. Well, since my maximum for the parabola is 6, I'm now including my local max, my absolute max as well for that. So I'm concerned. I'm having that constraint, and then I can go x. What did I say? 10. And then y3. What did we say? That was that big long cubic. That was my x to the third, and I'm just going to put dot 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 because I don't want to rewrite all that again. And that is going to be 10x to whatever I decide to go to get to the next graph. And so there's a local max at the first pink part. There is a local min at the second pink part. Also, somewhere in here is a point of inflection. I go from concave down to concave up. So somewhere on that black part of the graph, I flip to concave up again. Okay? Now, depending on where I go with this cubic, so now I'm concave up over here. So the next graph that I pick has to have a portion of it that's concave up. Okay? So it needs to be increasing and concave up. Whatever graph I pick, it has to go there. Now, this might be a place to pick another cubic to flip it. Because remember I said that you could have no more than 2 graphs of any which that are the same parent function. So I've now used an x squared and an x cubed. I could use one other x squared and one other x cubed in my project to make this work. And then at some point I would have to flip to another polynomial maybe. I didn't say you couldn't. You could use all level of polynomials. I just double checked the rubric to make sure I wasn't talking over myself. I say at least 5 distinct curves, no more than 2 of any specific parent function. So at least 3 different parent functions are involved. I did not say they had to be a different class of graph. So they could be straight up polynomials if that's what makes you happy. And so this project could be a lot easier, it could be a lot harder, just depends on how much energy you put into it and how cool you want to make it. Some of you are really excited to put in loops. You can put in loops. That would probably involve a graph that looks like that. Some kind of radius squared. And that would allow you to have some kind of a loop that would come together, and that would be fine too. So you're welcome to try to do that. You could also think about ellipses. That might be another option. The one place, I mean, that will be harder, honestly, to use things like sine and cosine. That one's going to be more difficult. Also keep in mind, look at the graph, whereas sine and cosine, you know, as it's written, is -1 to +1 in terms of the range. So you'd have to really work with your sine, shift it up way high, I guess, sine of x plus 10 or whatever, to get that sine curve shifted up to be able to use part of it. So it's possible. You just have to really, it would be a harder thing because it's not going to be as simple as solving polynomials. So not impossible, definitely not impossible, but potentially harder. Anyway, so that is how I would go about it. I got you through the first 3. You're not going to use mine. You're not allowed to use my graph. I hope none of you have already done this, because if you've used mine, you have to go back and figure it out because there's no way to prove who did it first. So I did not think about any of the constraints, the reasonability constraints I told you about in terms of highest roller coaster. I just picked numbers to show you that it could be done and how I would approach it in a way. Like I said, I got this done in about a half hour on my own. So yeah, I know different levels of education. I get that, but if I could figure out in a half an hour on my own, 4 of you in a group have 3 weeks to do this, along with your other half of your project, I think that this is a completely reasonable task, especially now that I've given you a huge hint on how I would approach it. So there you go.